Recording. Okay, Green's theorem. Green's theorem. Section 13.4. So, what is Green's theorem? Well, okay, Green's theorem, I'm going to highlight it right here. Green's theorem gives the relationship between a line integral around a simple closed curve C and a double integral over a plane region D bounded by C. Okay, so, line integrals, we compute line integrals over curves. But what if the curve is a closed curve? If it's a simple closed curve, okay, with what's called positive orientation, then we can compute the line integral using the Green's theorem. So this would be example figure 1. Okay, figures 1 and 2. Hold on here. Yeah, they give simple closed curves. I want to make sure this shows nicely. So, well, let's look at figure 2. So figure 2, you have a closed curve C. Okay, you see how figure 2 in A and B, you have two figures, and both figures have closed curve C that surround a region D. Well, the closed curve C in part A has what's called positive orientation. The movement is counterclockwise. That's positive. No, I'm sorry. Hold on. I didn't see it well enough. Yeah, in A, positive orientation, the movement is indeed counterclockwise. And in B, the movement there of the particle C is clockwise. That's called negative orientation. Okay, so this orientation, positive, negative orientation, is going to be important. So what Green's theorem says is the following. Okay, Green's theorem says the following. I'd like to highlight all that. Yep, good. So let C be a positively oriented, piecewise smooth, simple closed curve. Now that's a lot of terminology. I will just tell you for your homework, every curve you get is going to be a smooth, simple, closed curve. Okay, there are not going to be breaks in them or anything like that in the curves. The closed curve will contain a region D. The region D is bounded by the closed curve C. If P and Q have continuous partial derivatives on an open region that contains this region D, okay, and again, region D, we think region of integration, right? A D is a region in the XY plane, region of that, and so this line integral on the left, okay, the integral, I mean, what is that on the left there? That is really the sum of two line integrals, one with respect to x and one with respect to y. That is going to equal then the double integral over region D, whose integrand is the difference between the partial derivative of q with respect to x and the partial derivative of p with respect to y. And they note there that the left side of this equation is another way of writing the work. It's what you're computing is work. The work that a force field does, and the components of the force field are P and Q. The work that a force field does in moving a particle one time around a curve, a closed curve C. That's what you're computing with Green's theorem. Okay? Are there any questions so far? Okay, well, let me ask you this. The partial derivative of q with respect to x and the partial derivative of p with respect to y. Okay, where did we see that before? Where did we just see that? In what section did we just see that? In particular, where we set them equal to each other. We saw that in the last section, right? Yes, that's right, Robin, section 13.3. When we wanted to show that a vector field was conservative, we would set those partial derivatives equal to each other. Well, in Green's theorem, if the partial derivative of q with respect to x equals the partial derivative of p with respect to y, what then is the integrand going to equal in Green's theorem? Or more simply, what would the double integral equal if the partial derivative of q with respect to x is equal to the partial derivative of p with respect to y in Green's theorem? We're going to have the double integral of d over, well, I want to be more careful. Simply put, if those partial derivatives are equal to each other, what's the double integral going to equal? That's right, Robin, 0. That's right, because the difference of the partial derivatives would equal 0. And so the work that the force field does in moving the particle once around the curve, this closed curve, equals 0. Now, how can that be? Why would that equal 0? All right, let me phrase it differently. Hold on, this is important. Let me go to the whiteboard. One moment here. Let me try to use my stylus today a little bit. I'm good either way, but let me try. Hold on. So much here on the desk. Okay, so Deodath, I noticed you just joined us, right? The exam information is posted in under announcements. I want you to take a look at it, okay? And then we can, I talked to the class about it, but we can talk about it as well, okay? A few modifications to the exam, all right? So, all right, just want to mention that while I got here. Okay, so Green's theorem, just wanted to mention that. This is a fairly small class, so I can, kind of know who's coming in and out, all that. So, okay, so Green's theorem, section 13.4. You're welcome. So in Green's theorem, we're assuming that the curve C is closed, and it's a simple curve, a simple closed curve. So, okay. All right, so Green's theorem then is this. And I notice on the left, that all this here, hold on, that's just equal to that's just another way of saying find the work. Find the work. Okay? Find the work that the vector field F does in moving this particle once around this closed simple curve C. Okay? Now, this is going to equal 0 if the partial derivative of Q with respect to X equals the partial derivative of P with respect to Y. And so that means that if this condition holds, okay, the work is equal to 0, right? Because this here is work, W. So if I have, okay, well, just kind of keep it simple here. Here's my curve C. The orientation is positive, right? This is positive orientation. Because we're moving counterclockwise. Positive orientation. Okay. And let's say we start here and go once around and we end here. So we start at that point. Okay, maybe I'll put the point in black. We start at this point. Okay. Let me just kind of label things a little bit. Hold on. Sometimes the mouse works better for erasing. Okay. So if, let me just be very clear here. Hold on. This is critical, that critically important. Okay, so the integrand here will equal 0 when those partial derivatives are equal. So that means then that the work that the force field does in moving the particle once around the path C is equal to 0. Oh, how can that happen? Why would that happen if these partial derivatives here are equal to each other? Why? Why is that true? Why does that make sense? Well, what does it mean? What does it mean if these partial derivatives here are equal. If the partial derivative of q with respect to x equals the partial derivative of p with respect to y, what's that tell you about the field? What kind of field is it? Okay, it's a conservative force field. That's right, Robin. And Eric is right. In a conservative force field, well, I mean, what's happening is the force field, it's a conservative force field. So along this path, part of the way, the force field's helping the particle move along the path, and some of the way, the force field's hurting the particle moving along this path. Okay, so see, I mean, do you understand that what I'm trying to do is I'm trying to help you see, you know, like we, you know, I give you Green's theorem. Here's Green's theorem, okay, and it's proven in the book, okay, but the proof is complicated. But we can at least appreciate that Green's theorem makes sense, because if we have a conservative vector field, then this by virtue of the fact that the partial derivatives q with respect to x and p with respect to y have to be equal for a conservative vector field. So we can appreciate that the work that a force field does in moving a particle once around a closed path would have to be zero. Okay, and so, you know, at least we can appreciate Green's theorem in regards to that. Does that make sense? Does that make sense? All right, is this helping? Okay, Eric, okay, good. I just want to I want to make these theorems as concrete as possible, you know. And they talk in the book how this theorem was proven by George Green. Let me see here if we can find in the book here the information about Green. I want to just try to find where they talk about, they usually, like in the textbook, they have information. Here we go. Here we go. Okay, so this theorem's named after George Green, self-taught mathematician, worked full-time in his father's bakery from the age of 9 and taught himself mathematics from library books. So, you know, back then in the, you know, 1700s, 1800s, they didn't have community colleges. And, you know, so, you know, now if you were born into a wealthy family, you could afford to go to school, but other folks, you know, had to just, you know, work at a trade. But this guy here, he taught himself math, and this came out of theories of electricity and magnetism. I mean, what I mean is he dealt in that a lot. In this book, comes across Green's theorem. He lived to age 40, entered Cambridge University as an undergraduate, but died just 4 years after graduation. Okay, so I just thought it would be nice for you to learn about the author of this theorem. And Green was the first person to try to formulate a theory of electricity and magnetism. How many have heard of George Green before now? Has anybody heard of him maybe in another class? Or okay, well, I just thought it'd be nice for you to see, learn a little bit about him. Okay, well then let us proceed on and look at a few examples. Okay, so okay, example 1. Okay, evaluate this line integral, where it's the sum of 2 line integrals, right? But it also stands for work. Evaluate this this work, where C is the triangular curve consisting of these line segments, two line segments, okay, one going from, well, three actually, 0, 0 to 1, 0, 1, 0 to 0, 1, and from 0, 1 to 0, 0. So here's a picture of this curve C. And let me ask you, in section 13.2, to compute this particular line integral, how many integrals would we need to do? How many integrals would we need to add if we were to use section 13.2 to do this problem? So section 13.2, you have a line integral along a curve C. So this full curve C here consists of how many curves are needed to make up the closed curve C? How many line segments are there? 3. That's right. So in section 13.2, you would have to compute 3 line integrals and add up those line integrals. Okay, and and you need to be able to do that. Certainly on the exam, you could see that, right? But in the case of a closed curve C, we can use Green's theorem. We don't need to add up 3. We don't need to find 3 line integrals and evaluate them and add them, because we have a closed curve C here. So, all right, the closed curve C shows a region D. Okay, and so here we're going to apply the Green's theorem. Okay, and in the Green's theorem, of course, the P function is x to the 4th, and the Q function is x times y, right? And so the partial derivative of Q with respect to x is just y, and the partial derivative of P with respect to y is just 0. And then the region D has upper and lower limits, y limits of 0 and 1 minus x, and then x goes from 0 to 1. Okay. So let me hold on. Let me get this down a little bit, and you get 1/6, and that's the work that the force field does in moving the particle once around that path, that closed path. Okay, are there any, hold on, I think I saw a chat thing here. Oh, okay. Are there any questions? Are there any questions so far on Green's theorem? All right, I'll mention something that I think is good to mention as well. In terms of notation, here, so sometimes when we have a path C with positive orientation, they put a little circle on the integral. They put a little circle on the integral. Let me just see here. On the second integral there, I don't think you can see it, but they have a circle that has like an arrow on it going in the counterclockwise direction. Okay, that's just another way of saying positive orientation. Right, so green stem's pretty straightforward, Let's look at another example here. Let me just see here if yeah, let's look at another example. Hold on. All right, okay. So we're not going to get too technical here. We can get maybe in our next class, next Tuesday, we can talk a little bit more about these figures. But let's just stick to the matter at hand. So, example four. Again, they want you to compute. Okay, what's this? What's this really mean? What are we finding here? Well, it's the sum of two line integrals, one with respect to x and one with respect to y. That's just notation. But what we're really doing is in example 4, is we are computing the work that the force field who has components, hold on, one moment on this. I want to make sure I'm saying this right. Yeah. What we're doing in example 4, when we compute this integral, is we're really computing the work that the force field with components y squared comma 3xy, okay, the work that force field does in moving a particle once around the curve C. And the curve C is a curve that encloses a region D in the upper half plane between the circles of circle of radius 1 and radius 2. Okay, and if we go to the picture here, here's the figure. Okay, figure 8. There's our curve C, and you can see it has positive orientation, and it encloses a region D. So, and again, it's important, I'll just mention this for the exam, it's important, to draw your region Ds. Sometimes I'll just mention this. On the last exam, a few people would do an integral, double integral, and they would put limits in, but wouldn't draw their region D. And there'd be no way to get that region, to get those limits right, really. I want to be careful. What I'm trying to say is to get your limits for your region D, I want you to draw that region D on paper. Okay, now you could maybe make a good guess and get the limits right, or in your mind you could do the limits. It's possible. I'm not saying it's not impossible. But for full credit, I want you to draw your region Ds on your paper. Okay, just like done here. Now let me ask you, we're gonna compute, you're gonna compute a double integral, right? Well, think about coordinates. Would rectangular coordinates or polar coordinates be better here? What would be a better choice for the double integral, given this figure 8, given this region D? What's a better choice, class? That's right, Christopher. Definitely polar coordinates. Okay, so polar coordinates, very good. That's what we'll use. That's what we'll use. And so in the problem then, okay, here they are applying the Green's theorem. And again, they just apply the Green's theorem, and the region D was between two circles, one with radius 1 and one with radius 2. And the limits go from 0 to of pi on those circles. So you get 14/3. Okay. Are there any questions on that? All right. All right. Then let me stop the recording here for section 13.4. Okay. And you know, 13.4, I wanted to just kind of work with some simple cases. Perhaps then next week we can talk a little bit more about 13.4. But let me stop there.